Very good morning once again. Welcome back to the class. We have last time talked about asymptotic notations, and I'm sure now you are getting a better clarity of programming as well as analysis. So as we have said that now we are going to go in more detail of design as well as analysis, and asymptotic notations are going to be playing a big role into the analysis part. So we have already talked of a big O notation. We have talked of a theta notation. We have talked of omega notation. We have also talked of small omega notation. We have talked of a small o. You might imagine that there will be something like as a small theta also, but yes, it will never exist. You can imagine because small o meant that equality to be removed, exactness to be removed. Omega meant lower than the lower bound, and big O meant more than the upper bound. So upper than that. And theta is always an exact bound. So small theta is never a notation which will be coming into picture. Then going further that now once I know these notations, given an algorithm, I want to find out its asymptotic notation. Given an algo, tell its big O complexity, or tell it's a theta complexity, or tell it's omega complexity. How to do that? So now, first method, in general, you could have a step count method like we talked in case of a insertion sort or selection sort. We talked insertion sort based analysis. So step count and then insertion sort analysis, we finally were able to find out all those situations. From there, we could even get cases of a best case. We could also get even case of a worst case. And then similarly, we could take average case. But what if step count is not obvious? For example, when I talk of recursive algorithms, how will you solve that? Not obvious. So what do you have to do? For example, I say any recurrence relation, recursive algorithms, recursive solutions. For example, we talked of a merge sort, we talked of a quick sort, we can think of a binary search, and many more like that. How to do that? All these have certain different ways, and we cannot straight away calculate the count because recursively we can't tell how many steps will be executed for step A or B, and then how many times, and etc. etc. Why? In this case, actually, the relation which we got was not linear or quadratic or obvious. Like in case of an insertion sort, I could say best case meant order, or because I could get a linear equation an plus b. In case of a worst case, I could get it as an square plus bn plus c, and like that. So then based on that, I can easily find out asymptotic notation. But for recursive solutions, the relation comes out to be kind of a recurrence relation. What is that recurrence relation? For example, in case of merge sort, we said if the time complexity of merge sort for size n is computed, because it has a recursive calls, so it is effectively equivalent to 2tn by 2 plus the constant which we used towards merging logic. So I said something like this. Now, the relation itself uses again t of different size. So total time complexity of based on n was being discussed, and we say it is recursively dependent on time taken for n by 2 into 2 plus n. For quick sort also, we could say that yes, in quick sort, best case, I could say it will become something like as a 2tn by 2 plus n. For worst case, I could say it became t of n minus 1 plus n. So tn is equal to tn minus 1 plus n. Again, t uses, again, same t with a smaller size of the n. So what is my recurrence tree? I always say, or recurrence relation. My recurrence relation always has the definition or answer of the calculations. I'll say if I'm talking of a time complexity based on size n, then it uses definitely something with a lesser than n size. Less than n, the same definition or the same time over a smaller input is needed in the definition, and along with this there could be some factor here, plus there could be some factor here, etc., etc. How to solve this? So how to find its time complexity? So for that there are three methods. First method, which is very simple but not very useful, is called as a substitution method. Second method, which is again very useful and quite generic in the nature, which we call as a recurrence tree method. So recurrence tree method. And the third method, which is a direct shortcuts, thumb rules, formulas available, is called as a master theorem. So for solving such recurrence relations, these three methods are useful. We are going to start with the first and second first, and then we will come to the third. First one is quite simple, substitution method. This method is what we are going to immediately touch upon. Effectively, it is a guess-based method. So guessing is never always easy or never always feasible, but it is effectively that I have to guess and then substitute. So I will say, for example, that if I say that I have Tn equal to, if I have a relation of saying that Tn is equal to 2T n by 2, even if ceiling taken or floor taken. So for the time being, I am taking floor, plus let's assume I have got some n. Something like merge sort. The only change being that I'm taking here, or I'll say not merge sort to be precise, maybe I can say quick sort. Why I am saying quick sort? Because here I'm taking a floor of that. So if n is odd, and if my pivot comes exactly at the middle position, so floor of n by 2 will be applicable for the left side, floor of n by 2 will be applicable for the right side, and finding a partition or finding the pivot's position will take n steps. So I have to solve this. So solution will mean guess what is going to be the final answer. What is going to be Tn equal to what of big O or something like that. For example, somehow I guess Tn will be order of n log n. How will I guess? Again, that's a big question. So either this will be based on, once you are experienced programmer knowing this kind of a relation, you will be knowing that this is going to be this, or by using a recurrence tree, or by using master theorem. Again, you will be able to compute fastly using master theorem maybe, so you can guess. But if you are a good programmer, intelligent programmer, you can guess smartly. But if you are able to make a good guess, only then you will be able to prove. So effectively, substitution method doesn't find the answer. It is helpful in proving that you have guessed correct. Prove that guess is correct. So this is what becomes the focus. So effectively, once you are able to guess, you have got half idea or majority idea, and then you will be able to prove that you are going in the right direction. So how do I guess? I said, let's assume P is n is O of n log n. What does that mean? It means mathematically, TO of n will be always less than or equal to Cn log n. If T is of this, it always means upper bound. Upper bound with equality also possible. So that is big O notation. So we say that it means Tn is going to be this. So how to now? So if guessed, I have to prove that I have guessed correctly. So how will I do? I said my Tn is 2t floor of n by 2 plus n. If I guessed, if Tn is guessed as less than equal to C of n log n, assume it is correct, C into n log n, guessed as this. So I will say, assume this to be true for n by 2. For size n by 2, if I assume it is true, that will mean I have Tn equal to 2t n by 2 plus n, and this answer I know via this. I said that I assumed it to be true for n by 2. So I can say, now I can substitute the value of Tn by 2 using guess. And because I have assumed the guess is correct, so I will say it is equivalent to saying that this will become less than equal to 2 into C, n is n by 2, floor of that, into log of n by 2, floor of that. Later we will remove the floor, but intentionally I'm just continuing with floor, that even if a floor is there, still you can pursue. Of course, for a rough approximation, floor doesn't make much of a difference. So I say Tn is going to be this. Ultimately, I have to prove it mathematically and solve it mathematically to get mathematically solve it and reach to prove that this will solve as Tn will come as less than equal to Cn log n. If I am able to have something like this proved, then I will say that yes, I guessed it correctly, because I have said that I assumed this as a guess. For n by 2, I assumed that correct. Using n by 2, something like mathematical induction, using n by 2 as correct, am I able to prove it for correct as for n also? Then my proof will be over. Let's try to solve that. This is equivalent to, I can say C into 2 into n by 2. So if n is odd, n by 2 is less than odd. So I can say if n is odd, 2 into floor of n by 2 will be probably lesser than n, but otherwise it will be equal to n. But if already I have equality or less than equal to, so even if I write here C into 2n, I can easily write, because 2 into n by 2 definitely will be either if n is even, it will be exactly n. If n is odd, then I am going to have this value to be equal to effectively n minus 1. So minus 1 there, minus 1 can go to the other side, and with equality or less than equal to, that minus 1 can still adjust without a difficulty. So I can say Cn into log of n by 2. Again, floor of that will take either exactly as even value of n or multiple of 2. Otherwise, will be small, slightly lesser, and that with less than equal to adjust. Let's try to further solve it mathematically. That is C into 2, sorry, this becomes n, sorry, not 2n, and 2 and 2 will cancel. So I will say this is C into n into log n minus log 2. Just this line I'll remove. So I can still say this becomes the Cn log n minus Cn into 1. So I can easily see plus n was obviously earlier written, so that n will still continue. This n I forgot to write. I'll just remove this whole so that you don't get confused. So this n is still there, and I say plus n. So I can easily say Cn log n minus n into, I can say, 1 or c minus 1. Minus I have taken common, so I can say c minus 1. Now, this is one answer, but I have to prove it to be something like this. So I have to now further change inequality. So my inequality is Tn equal to less than equal to Cn log n minus I have got n into C minus 1. Now, minus C into n into C minus 1. If I can say, if C is greater than equal to 1, then I can guaranteedly claim that nc minus 1 will be positive or 0. If C is greater than equal to 1, this value will be positive or 0. So if it is a positive value in mathematical inequality, I can easily take it to the other side, as this value is positive always, less than equal to Cn log n. Now, from here, I say, in general, if x1 plus x2 is less than equal to x3, and if this value is positive, I can guaranteedly imply that x1 is also less than equal to x3, because x2 is a positive value. This side was already lesser. Removing a positive value will make even lesser. So lesser relation will continue. And if x2 was, by the way, 0, earlier if it was equal, still it will remain equal. And if x2 was non-zero but positive, this side value, if that was already earlier lesser or equal, still it will guaranteedly remain lesser because I have further reduced the value. So I can claim from here that this will also imply Tn to be less than equal to Cn log n. So this is what assumption which we made has been proved. So I can say substitution method is what is this method. Obviously, you can easily see that this is not a very good method because we have to guess it correctly. Even after guessing also, sometimes there may be proof impossible or guess good and then prove is what is the formula. But this is proved in general. You have to also prove for n, and also prove for your initial condition, or I will say boundary condition. What does that boundary condition mean? That there is always going to be, Tn is always defined in two ways. One was I defined it as, let's say, 2Tn by 2 plus n if n greater than 1 or equal to, or I'll say if n is greater than 1, only then this relation works. Otherwise, I say it is equal to 1 if n is equal to 1. For n equal to 1, recursion doesn't work. Then I say it's a unit step, time step, unit complexity, and it can be solved without any recursive call, etc. So boundary condition means I must be able to prove it for n equal to 1. Boundary is n equal to 1. So I have proved this for n. Let's prove it for n equal to 1 also. Also prove also, I'll say, for n equal to 1. For example, I said T of n. Now I have to prove it for n equal to 1. Then I will say T of n be assumed to be C of n log n. In general, this is assumed. Now this is a non-recurrence relation. Substitute it for 1. Substitution for 1 will mean that this is assume it to be for, if I have said that I have proved it for n, so for any value of n, it should satisfy. For T of 1, this will become equivalent to c into 1 into log base 2 of 1. This effectively becomes less than equal to 0. But ideally, I know correct answer was actually correct is T1 is 1. I know that mathematically we have already defined that. So we are not able to prove for boundary condition. So there can be a situation that even if you have guessed correctly, proved it for n, but you are not able to prove it for 1, etc. So what will be the solution? For such situations, solution will be aim to prove it for some small value of n, might not be able to prove for n equal to 1. Say aim to prove for n equal to 2. I'll say aim to prove for n equal to 2, because for n equal to 2 also, it is closer to the same boundary. So I assume that sometimes for n equal to 1 proof was difficult. So we will say, let's aim to prove it for n equal to 2. N equal to 2 will mean, in general, the recurrence relation said this definition applicable, 2t n by 2 floor of that plus n. So substitute here, put n as 2, because this relation is applicable for n to be greater than 1. Relation will be always this. Recurrence relation is applicable for n equal to 2. So t of 2 is ideally equal to, t of 2 will be 2 into t of n by 2 is 1 plus 2. T of n is already defined. We have already said that t of n equal to 2t n by 2, etc., etc. If 2t n by 2 plus n, if n was greater than 1. So corresponding n as 2, this definition was applicable. But Tn is equal to 1 if n is equal to 1. So use this value here. It will become 2 into 1 plus 2. That becomes 4. So ideally, I should get T2 as 4. Correct answer, T2 is 4. I should be able to get this answer, get and prove this value using the guess. Prove this value using the guess. So this is what I am supposed to prove. So using the guess, what guess I made? I said Tn is effectively guessed as order of n log n. That indirectly meant that this is equal to Cn log n. That now substitute here T2. So T2 becomes less than or equal to C into 2 into log base 2 of 2. I can say it becomes C into 2 into 1. So I can easily say Tn will be, T of 2 will be nothing but less than equal to 2C. I want T2 to be 4. So if I say if C is equal to 2, I can easily get T2 to be less than equal to 2 into 2. So T2 is less than equal to 4. And I know that T2 is actually 4. So T2 is proved to be correct. So if my C is 2 or greater than 2, so my guaranteedly this relation will be more than 4 or equal to 4. So I am able to prove that. And assuming that C will be something bigger or C will be greater than equal to 2 is perfectly possible, feasible. So it's not a wrong assumption. Constant can have anything like this. So this is what is called as a substitution method in general. But as I already said, that this is not such a good method, and we have to probably think of doing a good guess. Sometimes even making a good guess could not be possible. For example, if I say Tn is given equal to 2t of n by 2 plus 15, and let's say plus n. Now, if I am given this, what should be the guess? What will be the guess? Even I might not be able to solve it in a good way. So I have to be a bit careful in this. I will say always consider n to be very large. This is a thumb rule. If you consider n to be very large, then I can say n by 2 plus 15 will be closer to n by 2 itself. Say n is 10 lakh. So 10 lakh by 2 will mean 10 lakh by 2 plus 15 versus 10 lakh by 2, more or less very close. So approximately I can say that approximately it is nothing but 2t of n by 2. And if it is a 2t of n by 2, then plus n, I can easily now guess it as n log n, order of n log n. So if I make a good guess, maybe I can put it here and then try to prove. So use this guess and prove it using substitution, and prove it for substituting for n by 2, etc. For n by 2 plus 15 to substitute accordingly in the right side, in the right hand side, and then solve it and then reach to solving it as Tn equal to sen of n log n. So this is what we have to do. So making a good guess will be always desirable, and after guessing, doing good mathematics and solving it will be another challenge which you have to do. But sometimes, even if you are able to guess, you might not be able to prove and work that. So, for example, I say Tn equal to T of n by 2 is 1, plus I say the floor or ceiling of that also being used, plus, let's say I have this relation. Now, what will be the guess? If you are a good programmer, effectively this means that for n by 2 with the floor side, if n is odd, you go to one direction and do some calculations. For remaining n by 2 or for upper limit of n by 2 with the ceiling, you go to another direction and plus 1 as a unit step. Effectively, it means, let's say something like I have a binary tree. One side have floor of n by 2, other side has floor of n, seal of n by 2 as nodes. And say I wanted to find sum of all elements in a tree. Sum of all elements in a almost balanced binary tree. Almost balanced, because if n is odd, then accordingly I will have something like this binary tree. So this is going to be something like this, where all elements are being added, and we will add on the left subside. Maybe I will add on the right, or I'll say reverse. Say this ceiling becoming, say I am saying that I am going to add on one side, add from the other side, and then add it with the root, and you get this. So ideally, the guess is going to be, it's its answer is O of n. So if I am able to make a good guess, still probably proving this might become difficult. Might be difficult. How? Let's see. What does that mean? Say I say Tn equal to On, assume as On. Correct. Assume it On, correct. So correct for n by 2. If I assume this to be correct, assume it correct for n by 2. That means Tn is actually always equal to Cn log Cn. That's it. Cn, because it is order of n. This is what we assumed. For n by 2, that will mean it will be equivalent to saying that a T of n by 2 will be called to be C of n by 2. Now this I will substitute in equation 1. Which one is equation 1? This is my equation 1. So this is my equation 1. In this equation, I will substitute. So I will say Tn will be less than equal to C into n by 2 plus C into n by 2 plus 1. Effectively, you can easily see that it will become less than equal to Cn plus 1. So what we got mathematically is Tn to be less than equal to this. Because this is a positive value, I can say Tn minus 1 is less than equal to Cn. But we wanted to prove that Tn is less than equal to Cn. We wanted to prove Tn to be less than equal to Cn. And I can't claim that Tn minus 1 can be still said to be Tn. No. So, not able to prove, although guess was okay. Still not proved. So, some situations like this will always come and we have to handle. So, we can say substitution method is not, again, a very good method. Similarly, not only that, in this case, maybe we have to play smartly. So maybe instead of saying that I guessed it as Cn, I will say probably I can guess it as Tn to be not just less than equal to Cn, guess it as Tn to be less than equal to Cn minus b, where b can be some constant. So if you assume this as a guess and then use this guess like this and then prove and substitute and prove, so you will be probably able to reach to the answer. So you can have some, so all this is now not straightforward. You have to play smartly. So you have to be smart in guessing, and then you will be able to do that. Of course, for more detail, read in the Coreman book. Many examples are given. Read examples and solved examples for this. You will get a lot of additional information also. So this is one thing. Not only that, sometimes changing variables can solve the problem because we are not able to directly solve. Can be one way. Another smart move. So you have to be probably thinking of out of box also. So can be another smart way or method. For example, if I say Tn is, I am given as Tn equal to, mathematically I am somehow able to find out 2t square root of n plus I have got log n. Now, how to guess? No idea. I can't really probably guess. I am not able to think what will be the solution. So I say, assume n as equal to 2 raised to m. And that change the variable. So change variable and then solve it. Change variable n to m first, and later m will be replaced by log m. So solve for m and then m will be replaced by log m. So this effectively will mean this becomes 2t into 2 raised to m's square root plus log of 2 raised to m. So now you can keep on solving. You can easily see that once you solve it, you will be able to get it into accordingly solved, and then you can mathematically prove this. Later, you will have some relation in terms of S of m, and then later you will solve and replace m as log of n. Sorry, just 1 second. Let me take water. So how to do that? You can easily see that I have got this. Effectively, I can write this is equal to 2 raised to m by 2. Square root of that is being taken. So if I have got the corresponding value like this, plus this solved as log base to 2 raised to m effectively means m. So in this, now I will say this effectively I can solve by taking correspondingly 2 raised to m s of this. So I will say t raised to I'll say that t of 2 raised to m will be considered as s of m, and then now I will be able to solve this and then do this. So I will be able to get a solution to this. So with this process, there can be many such smart ways, and you have to ultimately try all these ways, and many such smart ways are possible. So for detail, read always the book, Corman's book, and you will get much more details from there. Read this. Then we are going to talk of a recurrence tree, which is a more useful and more systematic method. More systematic and more useful method. So next 30 minutes will be needed to discuss that and more useful and generic methods. So let me just stop here and stop recording.